I'll make the general, oh, sorry. I was going to make the general announcement. Do we have everybody here?
Just about. We have a few absences for sports today.
Okay. Well, then I will make the announcement officially, and then I'm going to put it on Canvas also. So Monday from 11:30 to 1:30, DMART and I will be in the atrium, the Stites atrium, for you to pick up the supplies for week two's lab, and to be able to purchase the laboratory notebook. As I understand our COVID protocols for these 2 weeks, everybody is supposed to be on campus for week 2. So we will be there. As far as the cost of the laboratory notebook, it's $13 for a 100-page notebook. I don't know if DMART has any 50-page notebooks left. I will be checking with him later today to see once. The 50-page ones would be a little bit less, okay? Any questions about that right now? And for those of you who are still not going to be on campus next week, yeah, send me an email. Let's talk. Let's figure out something. Okay, thank you.
All right, good deal. Let's go on with our announcements. Yeah, and if you're here, you can turn your camera on if you want your instructors to feel like they're actually teaching a real class to real people. That would be cool, and we'd love that. All right, other announcements. So it looks like most of you completed the homework that was due last night. Excellent job. I think I saw 44 out of 45 students completed it, so way to go. Tonight, the syllabus quiz is due. I think about 30 of you have done that, and everybody who's done it has gotten 100%. Not meant to be memorization, just meant to bribe you into looking at the syllabus. So open the syllabus and have a look and complete that quiz on Canvas by tonight. And then this weekend, you'll have your first quiz to work on. So these quizzes are going to vary in their format. Some of them are going to be on Chem 101. Some of them are going to be on paper and submitted on Canvas. So you'll just have to wait for the update until the day before. This first one is going to be on Chem 101. So if you've looked under the quiz tab on Chem 101, you can see the quiz 1 is there waiting for you. It's locked until after class today. It will open, and you'll have until Sunday at 11:59 to do that. So remember that the rules for the quizzes are you can use your notes and anything that you've taken during class, but you can't collaborate with us or with any of your peers. So you do only your own work with no help from your peers or the internet, but you can use your notes to complete that. There are 6 questions. They're multiple choice. You'll have 30 minutes. We've only really had 1 lecture so far, so not too much to worry about, only that first Wednesday content. Okay, so you have that to work on this weekend. Remember that you have to go to Rachel, Graham, or Mike's open hours at some point during the first 2 weeks. Mike wants you to visit him. He's sad and lonely in his office, and he has had dental work, so he really needs a pick-me-up today. So you should come hang out with him. 6 people came to see me so far this week, and that was awesome. It's nice to have a chance to talk with you guys. So make sure to check that off when you have a little bit of time. And then there's that reminder about lab supplies. You will need a lab notebook, so you'll either get it from us or from somewhere else. Okay, questions about upcoming assignment deadlines? Nothing mysterious. The only new information is the Chem 101 thing. All right, let's see. So we're going to start with a warm-up activity to make sure we all remember what happened last time. I will share. Oh, someone does have a question. Yes, question.
I was just wondering, are there any scientific calculators available to also pick up on Monday or not? I feel like I read that in the syllabus, but I might be wrong about their availability.
We are not selling any scientific calculators. So yeah, we're not selling any calculators, okay? What we do have is for those who forget theirs during a test, when we're in person again, and they forget theirs during the test, we can lend you one for that class period. Does that answer your question?
Yeah, thank you.
Okay.
Yes, there's also a link at the top of the Canvas course to an online scientific calculator, so you can use that one if you're working on your computer for right now. Okay, good question. Other questions?
Yeah, Bella.
So on your sheet, it said for the lab notebooks, did it say 11:30 to 1:30 for pickup?
Yes.
Is that what it said?
On
Okay,
Monday.
but on Monday? Cool, perfect, thank you.
Okay, you're welcome.
Yes, so right after our class until the 1:50 slots, basically. Other questions? I'm here for questions. Okay, if you have more questions, you can always put them in the chat and the TAs can answer those. So the first thing we are going to do is we are going to do a warm-up activity about the model of the atom, just to make sure we can drag back that information that we learned on Wednesday. So this is another PowerPoint activity that you're going to do with your breakout groups. You'll have 5 minutes to do it. What you are going to do is you're going to find your group slide, and in the black box, you're going to draw a rough model of the Rutherford model. So you can use the drawing markers in PowerPoint. You can use the like shapes, circles and squares and lines, items menu, however you want to do that. Give me a rough picture. And then there's a green box and a red box. The green box says known. You and your group are going to list some things that were known about the atom. Which particles did we know about? What did we know about them? Did we know their charge? Did we know their mass? Anything you can remember from lecture. And in the red box, it's called unknown. This is where you're going to list what we haven't discovered yet at the time of Rutherford's model. Please work with your group. So choose someone or choose everyone if you want. Everyone can dump things in, talk to each other, and then again, return to the slide with the blue boxes and write finished here when your group is done. So we'll be in the same groups as we were on Wednesday. So if you forgot, take a second, find your name on the list. We're going to be self-sorting again, hopefully with more success this time. And if you forget, this is on slide 2. All right, we're going to attempt to do breakout groups. Let's see how we do. Oh, hold on. We only have 11 groups. Okay, 12 groups. Participants choose rooms. Breakout room close. Yes, question?
Could you possibly open screen share, like allow us so we can screen share with each other?
Yes, I forgot to turn that on last time. I will do that right now.
Thank you. Because sometimes I can't get it up, like it's just not loading and I can't see what's going on. So that'd be great. Thank you.
Excellent. Yes, go ahead and join your breakout rooms. You have 5 minutes. So I see lots of circles going on here. I see lots of like positively charged things inside of a circle in the middle. I'm seeing some electrons around the outside. Good. Okay. Hopefully that served as a good warm-up. Remember, the Rutherford model was the discovery of the proton as a small, heavy, dense particle inside of the nucleus in the center. We knew the electrons were present somewhere, zooming around the outside. Not a lot of info about those yet. We did not know about neutrons yet. We didn't know about isotopes yet. We didn't know about Schrodinger's model or anything that we haven't talked about. So good work on your warm-up here. We can go ahead and get started on today's lecture, moving on from that point on. Let's see, here we are in the schedule. We are here on day 3. Oh, and I should give an update that Graham, his family member, is doing a little bit better. It sounds like he should be back by Monday next week. So hopefully things are looking better and he'll be able to join us again. All right, here's our list of learning outcomes. So I checked off the ones we covered yesterday. We have a couple new ones we're covering today. So today we are going to be able to count the number of protons, neutrons, and electrons in a chemical symbol. We're going to be able to contrast isotopes. We're going to be able to calculate the average atomic mass for a particular element, to recognize that the atomic mass is not the mass of any actual atom. And then we're going to do a little bit of nuclear chemistry in the second half, We'll identify different types of radioactive particles and radioactive decay processes. We're going to balance nuclear equations, talk about productive uses of radiation in nuclear chemistry and society, and then we'll learn how to predict what type of radioactive decay a particular nuclide might undergo. So, some cool stuff that we're going to be doing today. But before we can talk about cool nuclear chemistry, we need to know about chemical symbols. So let's start there. So last time we learned about what's inside of a nucleus, how the number of protons is the most important part to determining the element, but we also have neutrons and we also have electrons. But we can't go writing all of that information out every time we want to talk about an atom, because that just gets to be too slow. Y'all have seen me write during these lectures and you know how long it takes to write things. We just don't have that kind of time. So we can't write out the name of an element and the total proton, neutron, and electron count every time. So what we need is a condensed version. And that condensed version is called a chemical symbol, or sometimes it's called an elemental symbol. Sometimes it's called a nuclear symbol, because it represents one nucleus. So you've seen these chemical symbols before. These are the things that you find on the periodic table. So you might have seen the chemical symbol C for carbon. You might have seen the chemical symbol Na for sodium. They're not always the first two letters of the element's name. They can either be one letter or they can be two letters, but only the first letter is capitalized. And so this tells us about which element it is, but we can also include some other numbers to tell us about how many protons and neutrons and electrons we have. So you might see carbon written like this. We have numbers we can put in the top and bottom, left and right corners, technically except for the bottom right corner, that can tell us about that information. And I'm going to write a generic element here with the generic symbols. Unfortunately, there is not an element with the chemical symbol X. Maybe someday. There are still more elements being discovered every year. So I'm holding out for J myself because people with J in their name can't spell anything because there's no chemical symbols with J in it. Okay, so let's talk about which numbers go where. So the Z, the number in the bottom left corner, that one is called the atomic number. And the atomic number is the number of protons in that atom. And as we know, the number of protons defines what element it is. And so because the number of protons defines what element it is, and so does the chemical symbol, the letters here, we don't actually need both of them because they give the same information. So this number in the bottom left is often omitted. We often leave that out. Then the number in the top left, that one's called the mass number, represented by A. And this is a count of all of the particles in the nucleus that contribute significantly to the mass. So remember that the proton and the neutron, those were pretty heavy, pretty similar in mass, but the electron was 10,000 times lighter. So we don't need to consider how many electrons there are when considering how heavy or how much mass the atoms have. So the mass number is a count of the number of protons plus the number of neutrons, everything in the nucleus. And then in the top right, we've got the atomic charge. As far as I know, there's not a generic symbol for this one. So I just wrote the word charge. And this is a way of representing the net difference between the positive charges and the negative charges. So the positive charges come from the protons. So it's our number of positives minus our number of negatives, and the negatives come from the electrons. So while you might think it would have made a lot more sense to just have one number for the proton count and one number for the electron count and one number for the neutron count, in terms of chemical properties, I promise it makes a lot more sense when doing chemistry to have the proton-neutron sum and the proton-electron difference. It just means there's an extra step for you if you want to figure out how many of a particular kind of particle there is. So let's make another couple notes about the charge, because we're going to need to know more about that in the next chapter. So remember, in all those experiments in Harry Potter and the Evolution of Atomic Theory that we talked about on Wednesday, most of those experiments relied on the charge of the atom to learn more about those subatomic particles. And we know that most atoms in their neutral state don't have a charge. And that's because they should have equal numbers of protons and electrons. But not all atoms are neutral, as we know by the fact that I listed a charge on this sodium up here. And so if an atom does not have the same number of protons and neutrons and it has a charge, we call that an ion. So ions have charges. And so there's a different type of ion, whether there's a positive charge or a negative charge. So if the atom has a positive charge, we call it a cation. Just like a cathode, if you're talking about electricity. And so in order for this to have a net positive charge, that means the number of protons has to be greater than the number of electrons. And as we'll talk about in the next section, most of the time, nuclei do not just randomly gain protons, because number one, that's very difficult to do, and number two, that would fundamentally change what the element was. So when we say that a cation has more protons than electrons, it attains that status specifically by losing electrons. More on that in chapter 3, but electrons are the currency of the atom. They're traded back and forth in order to balance charge, to complete reactions, and to form bonds. Okay, so cations are the positively charged nuclei, and if you have a negatively charged nuclei, it's called an anion. This is a great crossword word, by the way, because it has a lot of vowels in it. I use this in the crossword all the time in my quest to become an old person. And so anions have a negative charge, which means the number of protons is less than the number of electrons. And since we don't gain or lose protons in most normal situations, if we have extra electrons, that means we have gained electrons. So far, so good. Everybody loves a little bit of terminology. Okay, so now that we have all the terminology we need and we know what all the different numbers and the chemical symbols mean, now we need to have a go at it. So here are two nuclei. We've got copper 64 2+, and we've got carbon 12 1-. We need to figure out how many of each of them there have. So why don't you guys try this one on your own? So I'll give you 1 or 2 minutes, work on it on your paper, see if you can figure out how many protons, neutrons, and electrons each of those has. Then we'll talk. Okay, does anybody want to tell me for copper, how many protons that copper has? You can unmute yourself or you can put it in the chat if you want.
Copper, I got 29.
29, good. Okay, that comes from our atomic number here. How about my number of neutrons?
35.
35, okay, so we take our mass number of 64 and we subtract the 29 protons, and that should give us 35 neutrons. How about my number of electrons?
27.
27.
Good, 27, and we get that from our charge here. So this one, you got to do a little bit of mental math. 29 positives minus something should give us +2, and so that something needs to be 27. So there are 2 electrons that were lost from this copper atom. Okay, what about for our carbon? How many protons does the carbon have? Okay, the chat is blown up. 6. That
Yep,
one is the
6.
easiest one. Listed right next to the nuclide. Most of the time it won't be, and you'll need your periodic table. But for today, it is. How about neutron number?
6 is blowing up again.
Okay, also 6, right? Because the carbon 12 minus 6 protons is 6 neutrons. And then how many electrons do we have?
Oh, that looks good.
7.
A lot of
This
7s.
It's easy to mix up. Sometimes when you see that negative charge, you think that you might have lost electrons because it's a minus sign, but remember that every electron you gain is worth 1 negative. So extra negative charge means you have extra electrons. Very good, very good. Y'all are rocking it. Okay, so now we're gonna do another 5 minutes in the breakout group. There is a Chem 101 activity waiting for you, but first we're gonna do the Chem 101 attendance. Everybody pull up your Chem 101. There should be an activity under the in-class section that's called attendance. And the code for today is 2000, 2000. So you need to go to that activity and type in the number 2000 to be able to access the activity we're doing today. All right, keep going. We got 29 people. We have 32 people. I could just sit here and watch the numbers change forever. And I do. It's a bad habit.
35, 35. Do I hear 36? Do I hear 36? 36, 36, 37. There we go. Aiden, what's up?
Is this on Chem 101?
Yes.
Okay, thank you.
Okay. Under assignments.
Yes, under in class, there's an assignment called attendance. You want to click on it, you want to put in this number. I should probably do this at the beginning of class. That would probably make more sense. We'll try that for next time. Okay, we'll leave that open. If you are ready and you have your code in, I'm going to publish this activity called Day 3, Activity 1. And then y'all can jump into your breakout rooms and you'll have 5 minutes to work on the 3 problems in Activity 1. Go forth.
Looks like we're stuck at 43 of 45.
Meeting is being recorded.
All right, everybody's back. Good work there. Just for the record, if you don't get through all 5 of the in-class problems, it's okay. It's just there for you and your group to promote discussion, give you a chance to practice what you're doing, give you a break from listening to my lovely voice for 70 entire minutes, as we all need. So looks like most of you guys got through the first 2, and some groups got through the last 3. So good work on that. We'll move on to the next topic. I keep Chem 101 open. We're going to be heading back to that. All right, so now that we know about chemical symbols, let's go back and talk about what the heck are these isotopes that we mentioned in our Harry Potter and the Evolution of the Model of the Atom. This blob is supposed to be the periodic table, which we're going to come to spend a lot of time learning to know and love in this class. And so a lot of those pieces of information from the chemical symbol are in these little boxes on the periodic table. So let's talk about what those numbers mean for carbon, because carbon is awesome. Why not? So let's do a blow up of that box for carbon. So the box for carbon looks like this, or at least it does on mine. Okay, so an anatomy of one of these boxes will recognize this number. This is our atomic number for carbon. Every atom of carbon, no matter which isotope, is going to have 6 protons. We've got our chemical symbol is there in the center. We have the name in whatever language your periodic table is in. If you look on the wall behind me, I've got a Chinese periodic table, and each of them has their own character. And then this number at the bottom looks kind of like the mass number, right? Our mass number for carbon on the last one was 12, but it was 12 even. Is this the mass number, 12.011? Answer is no. This is something similar, but slightly different, called the atomic mass. So that brings us to the question, why? Why did we not list the mass number there? It would have been really useful. Why is this number so close to the mass number, but not exactly the same? And the answer to that is that it has to do with the fact that there are multiple isotopes of carbon. So let's define isotopes, and then we'll answer our question. So isotopes are atoms of the same element, which we know because atoms of the same element have the same number of protons. That is the definition of what an element is. Atoms of the same element with different numbers of neutrons. Neutrons are really underappreciated in the nucleus. They don't have a charge, and so no one really cares about them, but they're really the key to holding that nucleus together. So these isotopes are going to have different mass numbers. So for example, since we're talking about carbon, the most common isotope of carbon is carbon-12. When we're reading a chemical symbol, we read the name first, and then we read the mass number after that. So carbon-12. Carbon-12 has 6 protons, 6 neutrons, and then this is going to be its percent abundance. Out of all of the carbon in the known universe, 98.89% of it is carbon-12. So percent abundance, I'm going to write my key over here because my planning was not awesome. Neutrons, protons, isotope. So this is one isotope of carbon, the one we talked about on the last page, but there are other isotopes of carbon as well. There is also carbon-13, and there is carbon-14. So we'll make a table for the info about all of them. So because these are all called carbon, that means they're all going to have the same number of protons, so we can fill that part in. You can find the number of neutrons from the mass number. Take a second, think about it in your heart. 13 minus 6 is 7 neutrons. 14 minus 6 is 8 neutrons. And then the percent abundance, carbon-13 is found at about 1% of all carbon atoms, and carbon-14 is very rare. So we're just going to write trace amounts, which is code for essentially 0. So most of the carbon is 12, but there is some carbon that is in the form of carbon-13 with an extra neutron, and a very, very small amount that have 2 extra neutrons. So back to our question, why atomic mass and not mass number? The atomic mass is a version of the mass number that represents all of the different isotopes of that element. Specifically, it's a weighted average. You might recognize the term weighted average from the way you calculate your grade. If you have an exam category worth 30% and homework worth 70%, you would take your percentage or your weight, multiply it by your score for the category to find your overall grade. That's the same kind of thing we do to calculate atomic mass. So the formula for atomic mass looks like this. It is a sigma, which means the sum of all the terms that look like this, the isotope mass, which will be given, times the fractional abundance, which will be given to you either as a fraction or as a percent. One of those math skills we need for this class is converting between decimals and percents. Okay, so far so good. We've got one example problem here to make sure we're all comfortable with the math, and I've pre-written it because that's just how my life is going right now. So this example says the three carbon isotopes from the table above, here are their masses: 12.0000 atomic mass units, 13.0034 atomic mass units, and 14.0032. So with those masses, find the overall atomic mass. So we're going to take the isotope mass for each of these and multiply it by the fraction version of the percent abundance. So I'll do it with you. So we're going to do, the first one is carbon 12, which has a mass of 12.0000 AMU. Its percent abundance was 98.89, but we want the fractional abundance. So we're going to divide that number by 100 to get 0.9889. And then we'll do one of these terms like this for each of the different isotopes. So for carbon 13, 13.0034 times 0.0111 abundance. And then for carbon 14, has a mass of 14.0032, and trace amounts is essentially 0. So we'll just go with 0. You can type that into your calculator, and you should get 12.011. So that is where the atomic mass on the periodic table comes from. It's a weighted average of all the masses and abundances of each of the carbon isotopes. And one note that I would like to make, note that the atomic mass of carbon is 12.011. None of the actual atoms, none of the possible isotopes have a mass of 12.011. This is not the mass of any carbon atom that you will find anywhere in the universe. It's just a weighted average. We only use that number because it represents all carbons in the universe. But no carbon atoms actually have that mass. That's like my favorite true-false question to put on quizzes is, does any carbon atom actually have a mass of this number? So it's an average. And even if you don't know the percent abundances, you can use that average to give you an idea of what the mass of most of the atoms will be. Because remember, this is a weighted average, and so the number, the 98% carbon was 12, and the overall atomic mass was 12.011. So we can make a guess about what the most common mass number would be based on that average. Most atoms will have a mass number close to the atomic mass. So we can guess that most of the carbon in the known universe is going to be carbon 12, which was true because we said it was 99% of all carbons.
So Rachel, what is the importance of carbon 13? How is that important to us?
Carbon 13 is radioactive, isn't it?
Yes. And there's this thing called carbon dating. Isn't that based off of carbon 13, the carbon 13 decay?
I believe so. That's how we know how old the Earth is.
And when you take organic, okay, and a lot of you will be taking it, carbon 13 plays into looking at the structures of compounds. when you're using NMR. So just a little aside as you're writing things down and you're going, what? Okay, sorry.
Fun facts with Mike about chemistry. All right, we have another 5-minute Chem 101 activity to do in our groups about this page. So I have opened it. I'm opening the breakout rooms. Go forth for 5 minutes and practice atomic mass.
Activity 2, is it published?
Yes. May have to refresh.
Ah, that's why it's not working for me.
Sometimes you have to.
There it is. Yep.
Okay, looks like Aiden's dropped out. Aiden should be in room 9. Oh, there he goes. Okay. All right, so now that we know about how to write chemical symbols and we know about the different isotopes that exist for different elements, let's talk about nuclear chemistry, which, by the way, is not usually covered in this course. It's a new topic, so if you go to tutoring and you ask them about it, your tutors are not going to know anything about this. So keep that in mind if you go to tutoring about this lecture. Okay, so, whoa, there we go. There's something underneath my paper and it's messing up my handwriting. There we go. Okay, so we learned about atoms of different isotopes, and you may wonder to yourself, why is it, Rachel, that carbon-12 is present in 99% of the carbon atoms in the universe and carbon-13 is only 1%? What is it about carbon-13 that makes it inferior? And the answer is that different isotopes have different levels of stability. And so when we're talking about a particular nucleus of a particular isotope, we're going to call it a nuclide. It's similar to the word nucleus. So these different atoms or these different nuclides have varying levels of stability. If you want to learn more about why, you are welcome to read the textbook. We don't have time to go into the full story, but the full story has to do with the fact that it's actually very difficult to hold a whole bunch of positively charged protons together in a small ball because they repel each other. And so the different levels of nuclear force and different numbers of neutrons are required to help hold those together. So here is a picture that we can use to explain this. If you're drawing this on paper, the important parts to draw are the y-axis, which is, hold on, I'm going to scooch this over, which is the y-axis, the number of neutrons, the x-axis, the number of protons, and then you have this just like blob going down the middle with a smaller blob on the inside of it. So what this is this is a plot of all of the different nuclides that exist, either found in the universe or synthesized in the lab. This yellow outline outlines all of the known nuclides, and the ones on the inside with the green dots, those are the non-radioactive, most stable nuclides. We have the non-radioactive ones in green, and the yellow is all of them, including the radioactive ones. And so what we call this green line that goes sort of down the center is we call this the valley of stability, that there is a certain ratio of neutrons to protons that makes a particular nuclide more stable. You can see here in red, this is the line of a 1-to-1 ratio of neutrons to protons. So you can see that for the smaller size elements, even with a little bit of glare there, that a ratio of 1-to-1 is the most stable. Those green dots are sitting mostly along the red line. But as we get to the heavier elements, a ratio slightly larger than 1 is the most stable. We're up here, it may be like 1.5 or so. And so what we want to talk about today is what happens if you have an unstable nuclide. What does radioactivity mean? What happens? And what are the different types? So we will return to this picture in a minute. Move that to the side. Come back to our notes. Okay. So new word, radioactive or radioactivity refers to the nuclides that are unstable or less stable anyway. So these nuclides that are less stable are eventually going to spontaneously decay into a different nuclide that is more stable. And that may be a more stable nuclide of the same element, or it may be a different element. This is the part of chemistry that you will not be able to do in the lab for a few more years because radioactivity requires special amounts of training and personal protective equipment. But you can actually turn an atom of one element into an atom of a different element under certain conditions and if you have enough energy available to you. So first, let's talk about the types of radioactive particles that can be emitted during these, by these radioactive nuclides. So I'm going to make kind of a sloppy looking table here. The first kind of particle is called an alpha particle. This is the Greek letter alpha. I'll write it here in case my handwriting is undecipherable. And so an alpha particle is has this chemical symbol. It's basically a helium-2 plus nucleus by itself. All the electrons have been removed, but an alpha particle has 2 protons and 2 neutrons. So it's this small group of nucleic particles being shot out of the molecule through the air. And this is considered the heaviest type of radioactive particle because it has a mass of 4 atomic mass units. And so if a stream of alpha particles is being emitted by something radioactive and you'd like to block those radioactive particles from hitting you, these can be easily blocked by a few sheets of paper. So this is the kind of particle, oh, I forgot to write paper, hold on. This is the kind of particle that Rutherford used when he was discovering his model. When he discovered the proton in the nucleus, he was using a radioactive material that produced a stream of alpha particles that were large and heavy. Then we also have beta particles. Kind of looks like a German letter Esset if you've ever taken German. Otherwise, it looks like a B with sort of a long stem. I feel like in the land of COVID, we're all sort of an expert on Greek letters now, unfortunately. So I guess there are some benefits. There are 2 types of beta particles. There's a positively charged beta particle and a negatively charged one. So we can write the negatively charged beta particle like this. It has a mass number of 0 and a charge of -1. So this is essentially an electron. So if the electron is living in the nucleus, living its normal atom life, it's called an electron. If it is being ejected out of a radioactive isotope, it's called a beta particle. And if it has a positive charge, we call it a positron, which is a positively charged electron, essentially. That is all that I know about it. I'm not a nuclear chem expert. I do not have the answers about what exactly a positively charged electron is, but we do know that it is very lightweight and it has a charge. And if you have a stream of beta particles and you'd like to prevent them from hitting yourself, you need to use a few more pieces of paper. So you need to use an entire textbook to block this. You need something a little bit thicker. And these type of particles are used in medicine. If you've ever had a family member who's had a PET scan, that stands for positron emission tomography, and this is what's used to measure your body and to look for areas of high activity, like tumors inside your body. The last type is going to be a gamma ray. Technically, it's not really a particle, it's just a photon of high energy light. More on that in the next chapter, but it's still worth including in this table. It has a mass of 0 and has a charge of 0. This is the lightest possible particle because it's technically not a particle, it's just energy. It's essentially massless. The reason I write essentially is that thanks to Einstein and his E = mc² formula, it does actually have a really, 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 really small amount of mass, but we don't have time to get to that today. So if you're interested, more in your textbook about E = mc². If you'd like to keep gamma rays from hitting you, you are going to need to surround yourself by 2 centimeters of lead on all sides. So it's very difficult to keep gamma rays from penetrating. You need to be inside of a basically locked vault or inside of several walled basements. It is difficult to keep gamma rays out of your home. So there is our attempt at a table here. And so if you have radioactive particles coming out of a radioactive substance, you can sort through them or determine what type of particle you have using the mass and using the charge. So here's a little picture of what that might look like. So this is a box with a slit, and this blob at the bottom, that's going to be something radioactive. Take your pick: plutonium, protactinium, thorium, einsteinium, curium, anything from the F block of the periodic table could apply here. Okay, so then radiation is coming out through the slit in the box. And let's pretend this radiation consists of alpha, beta, and gamma particles. Oh, I forgot to write the word for that. This is gamma, lowercase gamma. It kind of looks like a lowercase y if you squint a little bit. So if I wanted to separate these types of particles, one thing I could use would be an electric field, which I'm going to draw like they do in physics, like this, with two charged plates. Okay, so if I charge an electric field, the charged particles are going to move towards the side of the plate with the opposite charge. So our alpha particles have a positive charge. So out of this beam, they are going to start moving towards the negative side. And then if I wanted to block them, I could block them with a sheet of paper or a couple sheets of paper. All right, we're switching to blue. If we had beta particles in this stream, specifically if we had beta minus particles, the electrons, they would move towards the positive side, and they would be deflected more sharply than the alpha particles because they're lighter. So this is the direction the stream of beta minus particles would move. And if we wanted to block that, we would need to use lots of paper. Big, thick stack, like our OpenStax book. Many papers. And then gamma rays, there is no way to deflect them because they don't have a charge. And if you want to absorb them, you had better have some serious protective equipment made of lead. So there's our visual radioactive spider. Okay, I should really be keeping up on what's happening in the chat here. So if you're lucky, if you want to separate the particles, this is a way that you can do that. And then I have a graphic. Is everybody ready for me to turn the page? Let me return the view of your faces. Yes, okay, everybody's ready to turn the page. Okay, here is a page that is really hard to see. That is taken out of your textbook. So here's a series of different materials that these kinds of radiation can pass through. So the alpha particle is stopped easily by paper. Beta particles can move through paper. They can move through you and your hand because you are mostly made of water and thin skin. And it's stopped by metal. We didn't talk about neutron radiation, but this is a man-made type of radiation, can pass through paper, skin, metal, and is stopped by water. And then if you have gamma radiation, you can see it goes all the way off the page. It can pass through water, concrete, and people. It is only stopped by serious amounts of lead. Okay. So now that we've talked about type of radioactive particles, now we can talk about the types of radioactive decay. So how do those alpha and beta and gamma particles come out? And so each of these processes has a name, and each of these processes has an equation for the starting and ending nuclides. We can represent with a nuclear equation. And so the rules for these nuclear equations are that the sum of all of the mass numbers, those ones that are in the top left, and the sum of all the atomic numbers, those numbers in the bottom left, they need to be the same on both sides. Let's just say are, that's how grammar works. Are the same on both sides. Okay, and we have 3 minutes. So in the 3 minutes, we'll cover as many as we can. And if we don't get to them all, we'll finish it up on Monday. So the first kind is called alpha particle emission, which is just what it sounds like. It is when some radioactive nuclide emits an alpha particle. So here's an example of one. This is uranium-238. And if it emits an alpha particle, which is a helium-4, we are left with 238 minus 4 is 234. And 92 minus 2 is 90. And so if we look up number 90 on the periodic table, we'll find that that is thorium. So it produces a thorium-234. And so if you want to write alpha here instead of helium, you can. I like to write helium just to remember that it has 2 protons and 2 neutrons. And then we have special names for these. So the nuclide that's on the left side, the radioactive one that we start with, that one's called the parent. And the nuclide that is produced, not the radioactive particle, the other heavy nucleus, as far as I can tell, it is called the daughter or it's called the child, depending on what book you read. And so that's how we specify in a particular process which radioactive particle produced which other one. We can also have beta minus particle emission or electron emission, if you want to call it that. It's important to specify the sign on your beta particle since we have positive and negative particles. And so beta and minus particles are emitted when a neutron spontaneously turns into a proton, which I know is really mind-blowing. We've like just introduced the nucleus and its features and what lives where, and now all of a sudden I'm telling you that neutrons and protons are interchangeable. Remember, this is not something that happens every day. This is something that happens in a very small percentage of the atoms in the universe or made in a laboratory. So we can write it as the neutron turning into the proton, and you can see that 1 plus 0 equals 1, 1 minus 1 equals 0, or we can write it as the entire nuclide and think about imagining a neutron turning into a proton. So this is a nucleus of thorium turning into a nucleus of protactinium and emitting a beta minus particle. And we have a couple more to do, but we have run out of minutes and I don't want to keep you over. So we will put a cork in that and we'll save that for Monday. Everybody finished writing that part? Okay. So a few more minutes left to finish on that. We can finish that on Monday. Reviewing where we are. So remember to complete the syllabus quiz by tonight. Remember to complete quiz 1 on Chem 101 by Sunday at midnight. And good luck with your move back to campus. For those of you who are moving this weekend, it is going to be very, very cold. I think it's a low of -5 tomorrow. So be careful with your plants as you're carrying them into your dorms. Be careful with your face and your parents, and be careful if you're driving on your own.